Welcome back friends to your own channel. Today's video going to be super exciting. We are going to carry out exploratory data analysis in Python using the data that we generated in our last video. If you haven't watched that video, please do check it out before you come and watch this video. Also, a massive thank you to all of you for the amazing response on the last video. It's really motivating and very encouraging for me. If you haven't subscribed to my channel, please do it now. Also, please like, comment and share this video. It truly helped me. Before we begin, I want to show you the glimpse of today's session. There you go. Let's begin. Okay, so we are here on our Python notebook and this is part 2. To give you a quick recap, we have used World Bank data with the help of API calls. We imported WB data library for that and we have defined our different parameters as we've seen in our last video. So we have defined over 16 different parameters that we wanted to analyze. And we have defined our time frame, that is between year 2015 to 2020. And we have also filtered the countries for which we are going to analyze. We are not using all the countries which is available in data, but in particular G20 countries only. And our final data frame saved under name DFF, and that's where we stopped in our last video. Now to begin in today's video, let's try and explore data that we have. So let me show you. This was our data frame and let's start by seeing the top sample, dff.head. As we do that, it will give us the top 5 rows and I think we are fine with this. We have all the columns right now available here along with their respective data. So we are fine with the data. Let's see the basic information about the data and we can do dff.info. to see the basic information about the data frame. So we have a total 18 columns with us and we are having total number of records, that's 102 across this 18 columns. We have country and year which is of object data type, rest of the column is of float data type. Now here is the thing. So year is an object data type. However, we wanted this year column as an date time object. It's a specific data type in Python which we can use to manipulate date and time. So here in our case, it's date and time, which we are going to convert it now. But for all other columns, which is a float data type and which should be correct, there is no problem with that. And entire data set is occupying 14.5 KB. Okay. Let's convert the year into date and time object. And this is how we should do it. DFF year. And we're going to use Pandas library. So we'll call pd.to_datetime method. And here we are going to pass in our column DFF and year. Once we do that, yeah, it's going to convert it, gives a warning. If you don't want all these warnings to be appear on a Jupyter notebook, you can type following code. You can type from warnings, import filter warnings. And you can say filter warnings. You can ignore in case if there is matching warning which appears. And let's execute this. Once we do that, now going forward, if we have any such error which is coming up, it will ignore this warning. It will not show all these ugly messages to us. But right now, if we can see dff.info, and if we run our cell again, we can see that our year column is converted now into date and time data type from the object and which we can use it eventually, right? So this is basic information about our data set. Now we see that there are a couple of null values also. Maybe in inflation rate, there are null values, and poverty rate and maybe literacy rate has contained a lot of null values. So these are the columns which will not be very useful to us. We are staying away from inputting any kind of null values there. So for now, we are ignoring those columns which is having null values, right? Okay. Moving forward, let's get some descriptive summary of the data set. And for that, we're going to type dff.describe, right? And we're going to see this in an inverse manner to get a proper visibility of the data which it displays. I'll let me execute this cell for you. Once we do that, we get this descriptive 5-point summary for all the columns. Now, as you can see that gross domestic product column and gross national income product, GNI, so both are high in scale. They are 10:12, and hence all other columns you see are getting into some weird number, which is very difficult to manipulate. So now either you can analyze this particular table, which is very difficult. So rather, let's try and create two new columns like GDP and GNI with normalized scale. What we can do is either we can use z-score scaling to scale it down, or we can probably divide both the columns with maybe 10⁹, that's billion, and convert it to like $1 billion. So I think the better approach is to do it, convert it to $1 billion for now. So let's create two new columns where we convert this GDP and GNI. So let's call DFF, and here DFF, I'm calling this GDP underscore $1 billion. This will be my new column. And this will be nothing but DFF, and it will be gross domestic product divided by 10⁻⁹, right? Similarly, I'm also copying this code, and here we're converting GNI column into GNI $1 billion column, right? So that's our new column, and column in subject, which is gross national income. Once we execute this cell, we're going to get this GDP billion and GNI $1 billion column. Now, let's see how our descriptive summary has changed. So let's do the selected column, because we don't want again GDP and GNI column to appear on our descriptive summary and change the scale of other columns or change the way the table appears. So let's define selected columns, and selected columns is nothing but, let's say, they are all the columns from DFF except for the first 4 columns. So first 4 columns is essentially the country, year, the gross domestic product, and the gross national income. So we are calling columns which starts from index number 4 and all the other columns followed by. Once we do that, we can see our selected columns. As we do that, we'll receive all these columns under selected columns list. Now we can do DFF, and we can call selected columns, and we can type describe, and we can transpose this metric. Oops. So we do that, and we can, if we want rounded figures, we can do round again, and that will practically round it. So as we see that, now we have all the columns, which is purely readable. It is not in a weird format as we've seen previously. There are a couple of null values in here, this column, but let me show you how do we read this particular table. So we take any of the column. Let's say if we take life expectancy rate or life expectancy, that's in year. So the mean life expectancy for this G20 country for all the years is 77 years. That's a mean value. What it means that it takes all the record, and the mean value of all the records is 77. Now, the minimum value of life expectancy is 64 years in some year for any country, right? And the maximum value which you see for life expectancy, it is 85 years. So our distribution ranges from 64 years to 85 years with a standard deviation of 5 years on both sides, right? Similarly, if we take, say, mobile phone subscriptions, its mean value is 117 units, its minimum value is 76 units. It's go all the way to 167 units. So there is a large spread of the mobile phone subscription with a standard deviation of 22 units. And this is how we should read the entire table and get our insights. Let's say if we take GDP in $1 billion, the lowest GDP country in any year, which is 324 units, while the country with the highest GDP in any particular and all the years is with 21,381. That's the highest GDP has been seen in terms of $1 billion value. Let's move forward and understand more about this data in terms of their distribution, and we can understand distribution with the help of histogram. So let's create the histogram for all the numeric columns that are available with us, and let's try and gather some insights from there as well. So we wanted this histogram to be appear only on one screen and probably a subplot kind of arrangement where we can see all the columns histogram at one place. So let's try and type the code. So first of all, let's define our parameters. Let's say fig and axis, and this will be nothing but plt dot subplot. Within subplots, we're going to define number of rows is equal to 4 and number of columns is equal to 4, and we can also define fixed size, which we want as 14 by 10 unit here. Now this is our typical parameter. We also want to have a flattened axis, so we define axis is equal to axis dot flatten, and we'll iterate this particular histogram requirement through a code, and we'll say that for I and column in enumerate dot selected columns. So that's basically, it will take selected column, its index, and it will store in I and the name of the column. So we'll call sns dot histplot, and within which we are providing our data, which is DFF, and where X is nothing but that's our column, and we'll put KDE is equal to true, and in our case, the placement of this particular graph will be based on the column index which it appears, right? So it's in excess I column, and here we are going to define excess I, right? That's I index of the axis, and we say that set title is equal to name of the column to identify that this histogram belongs to this particular column. And we'll say that PhD, and we're keeping it tightly out to see it properly. We're also going to call it plt.show, and as we execute this, it takes some time to get executed. It has given us all the 16 graphs, basically 16 histograms for each of the column. As we see, inflation rate, unemployment rate, poverty rate, life expectancy, and so on. As we can see, there are a couple of graphs where we see there is appear to be symmetric, like for example, foreign direct investment or probably distribution of inflation rate. In some cases, like agricultural production index, although it's appear to be skewed, but slightly symmetric. Now, these are histograms, so you can find out like under which particular bin size there is more dense distribution or there is a higher frequency of records available. If you want to understand more about skewness, like whether the data is skewed or not skewed, what we can do is we can call DFF again, and can call selected columns, and we can do this skew. A skew will define the skewness of that particular column, and we can sort values. Right. As we execute this, we'll find the skewness of each of the column. Oops. Okay. Let's do this. Okay. So when we correct it, and we'll find it that literacy rate is having the highest skewness, so which is of -3.26. So it's left skewed. So if you see the literacy rate particularly, it's left skewed as we can see it, and it's having the highest skewness, like minus 3.26. And columns such as imports of goods and services, mobile phone subscriptions, and exports of goods and services, and government expenditure on education, and probably poverty rate. These are the columns which are having low skewness, and probably they are more symmetric. This is how you can define the skewness and can visually observe the skewness in your data with the help of histogram and skew method, right? Okay, let's quickly see the outlier proportion. It's important to understand outliers, whether they are truly outliers or there's some data errors. So let's check outliers, and one of the method you can check outliers is with the help of box plot. So let's create box plot in iteration in one basically subplot method. So let me just copy this particular cell and paste it here, and we are just going to change here the instead of sns.hisplot, what we basically want is box plot, and that's the only change which is required. We also do not require this kd is equal to true argument, because that's not the box plot argument. And let's execute this cell. As we do that, we'll receive the box plot for each and every column, and we see that for almost every column except for maybe mobile phone subscriptions and imports of goods services, exports of goods services, except for these three columns, I think there is outlier in each column. There's some columns where you find high outliers, which is like GDP in $1 billion and GNI in $1 billion, which is expected, because this is something economic indicator. Some countries are growing at much rapid pace and they're having higher GDP compared to the other countries. And however, access to electricity, now these are the G20 countries, right? So it is expected that access to electricity should be at higher level, but within that, you see the quite disparity, and you see the outliers even on the lower side. So apart from the outliers you have on inflation rate, unemployment rate, and so on. Now, these are the outliers visually you can see, but you still don't know what is the proportion of outlier in your data. If you want to understand the proportion of outlier and have to numerically capture that, we can probably define a function and can calculate whether each record is an outlier or not outlier. And we can calculate the number of rows out of total rows and consider it as a proportion of outlier in the data set or maybe in particular column. So let's define the function to do that. And let me name it as outlier proportion. Let's understand the outlier proportion here. So let's define the function called outlier. Yep. And our input will be x in this case. To do that, Q1 is nothing but our data. So x, that is our input, and we'll use this method called quantile. Right, and we use the 25th quantile as a Q1. Similarly, we'll define our Q3. Q3 again is our 75th quantile, right, of the quantile, and then we define IQR is nothing but my Q3 minus Q1. That's my interquartile range, and this function will return me whether my x is less than Q1 minus x is less than Q1 minus 1.5 times of IQR, or it will return me this, or it will return me whether x is greater than Q3 plus 1.5 times of IQR, right? So this is the function that we define here. Now, to calculate the outlier proportion, we can do like this. We can call a series like outlier underscore percentages, right? And which we define as an empty series here. And we'll call for each column in selected columns, right? So this will run through each column is there in our selected columns list. And we'll say that x is equal to DFF and the column name. And we say that outlier basically outliers is equal to outlier, and we provide this outlier is our function as we defined earlier, and we provide this input which is x, which is in the particular column. It will give us the outliers, whether how many outliers are there in the particular column. And as we do the outlier percentages, which is np.mean outlier, np.mean, and we do the outliers into 100, right? And we define outlier percentages, append outlier percentages. That means we are storing it in our data. So it will calculate the percentage of the outlier in that particular column, right? And next we'll store our result into maybe result data frame. So result data frame is nothing but it's pd.data frame. And within pd.data frame, we are defining the dictionary. So our name of the column is the selected column, right? And we are defining the outlier percentage, and that's our outlier percentage list, right? And we say that result.df is equal to result.df, and we're sorting this values. So we type sort underscore values here, and we want to sort values by outlier percentage. Right, and wanted to sort it ascending is equal to false. Okay, once we execute this now, we can see our result df, and as you can see that the outlier percentage, and we can round it off if you want. We can see that the outlier percentage in access to electricity is the highest, and then the agricultural land area, and so on. The columns like expectancy, mobile phone subscription, exports and imports doesn't see a lot of outliers as you have seen it visually, but here it's more of a numeric. So it's more of measurable, where we can see that the columns like access to electricity and agricultural land area having the highest number of outliers in the data set. Okay, and we can visually see this outlier percentage as well in terms of graph if we want to present to someone. So what we can do is we can set figure first. So we can call pt.figure, and we can call fig size is equal to 11 by 5, and here we say that sns.bar plot, and we say x is equal to result df, and then we say column, right, that's our x basically, and y is our result df, and that's our outlier percentage, right? And we can give name plt.title, and we can name it as outlier percentage. We can also rotate the text, because as we know that our column name is bigger, so our x-axis will be cluttered if we don't rotate it. So we'll say that rotation is equal to 90 to rotate our labels on x-axis, and then we can rotate plt.show. Once we do that, we find that this is the graph of outlier proportion, and similar to the table as we see, this is represented in terms of a nice beautiful graph. If you want to export this graph to your presentation, you can just right click on the graph, and you can do the save image as, and give it to any of your folder where you want to import it. Like in our case, I imported to desktop, and you can save it. Once you do that, it will download this particular graph for you, which you can open it separately and you can put it wherever you want to a particular folder. So that's a small tip from my side. Okay, moving forward, let's find out the null values in this data set. And how we can find out null value is with the help of isNull. You can do df.isNull, and we can do sum. That will give me the column-wise null values in my data. As I can see that poverty rate is having the null values, which is 67, which is more than 50%. And remember, on our data, total number of records we have is 102. So 67 is more than 50% in that case. And similarly, literacy rate is almost as high as 70% of the data, which is having null values. Right now, we are not dropping this, neither we are imputing it. Right now, we're just ignoring it for time being. But as you move forward and learn more about data science, there are many more techniques available to impute these columns in a scientific way. Or if there is a huge number of missing data, you can probably think of dropping that column as well. And for now, we are okay with the help of this check. So there are a couple of columns, like 3 columns where we find there are null values, right? So we are ignoring that columns right now. Okay, moving forward, let's understand correlation. Correlation is one of the important parameters that you would like to understand across all of your columns, how they are correlated with each other, and is there any high or low correlation, linear correlation in particular. And to check the correlation, it's very simple. You can call out your data frame like TFF, and you can say core, and that will particularly give you the correlation table for all the columns across all the columns, right? So if you see diagonally, it's all 1. Otherwise, it will give you correlation between 2 variables. So gross national income and gross domestic product is having correlation as high as 0.99. So that's like a clear, perfect correlation between these 2 columns. While if you see column like literacy rate and gross domestic product, which is having a correlation of 0.04, which is very weak correlation, right? But this is the dull table. If you want to visualize this table more effectively, you can use heat map from the Seaborn library to visualize this correlation, right? And let's set our figure first. To do that, and we say that fig size is equal to, let's say, 8 by 8. And here we're going to use sns.heatmap. And here we're providing DFF and selected columns, particularly, and doing correlation of it, right? We also want numbers to be displayed. So we'll put annotation is equal to true here, and a format will be of, let's say, 0.1 and float. So it's 0.1f. We also want some beautiful heat map. So probably we are using Turbo as a color map. You can choose your own color map for creating fancy visualization. And we do plt.show here. As we execute, it will take some time. It will create a basically correlation table into a nice heat map along with the color index. So as you can see that GDP $1 billion and GNI $1 billion is highly correlated, while the columns like, for example, access to electricity and unemployment rate, which is again inversely correlated, so -0.7. Now, government expenditure on education and life expectancy is correlated. They're inversely correlated, surprisingly, with correlation value of as high as 0.8, like access to electricity again, and life expectancy is again positively correlated. As you move forward, you need to understand the difference between correlation and causation. And that's why you need to understand whether this correlation is true or it's just a statistical fluke. Right now, we are not going into the topic, but you can study about correlation, difference between correlation and causation. And I'll try and put some link here in the description where you can go and read about those blocks. Right now, as we know that there are a couple of parameters which is having high correlation, either on positive side or negative side. Let's try and study those with the help of scatter plot. And let's call sns.joint plot. A joint plot is a good plot. As we see in our visualization video, we can use joint plot to visualize 3 parameters basically. So it will give you for the both parameters, it will give you the histogram as well as it will give you scatter plot for both the plots. And that's where we know that where the density of records available under which range, right? So let's call sns.joint plot here. and we wanted to see GDP, $1 billion here as a column. And let's see y is equal to GNI billion. And our data is DFF here. Our height of the chart I wanted is 4 units. And let's say color is an olive. Start with and duplicity.show. As we do that, we find that the chart is prepared and there's a clear linear relation as we can observe. However, we can also notice that the high amount of records which is concentrated in values less than 5,000. So above 5,000, probably these are the points where you find low density and they are probably the outliers, right? Similarly, let's also create chart, and let me just copy this code snippet which we can use it. So instead of GDP $1 billion, let's try and find out maybe gross capital formation. Capital formation versus maybe poverty rate. Poverty rate, and similarly we want the data. Let's slightly change the color. Let's call maybe crimson. Yeah, let's execute this. As we see that there's an inverse relationship between gross capital formation and poverty rate, which is quite intuitive here. We do not see in terms of distribution. They are more dense, so you don't see a lot of outliers here by seeing the joint plot. Similarly, let's also understand one more parameter, like one more pair of parameters. Let's say government expenditure on education and maybe life expectancy. Right? And let's change color to a bit, let's say blue color. As we do that, we find that again it's an inverse correlationship, and data distribution is largely on the side of like life expectancy above 75 years and government expenditure on probably less than 15 units. So that's the area, this particular area where you find a lot of data points, which is more concentrated. You can see it from the histogram of both the variables, and this is having inverse correlationship. So as government expenditure on education increases, your life expectancy decreases. That's a surprising correlation you find from the data available for this G20 country, right? Now, let's try and find out top 3 countries in each of the columns, like on across each of the years. So remember, we have a data from 2015 to 2020, all the years, and we have a different 16 columns. So for each of the parameter, how each of the countries are being ranked every year. So rather than seeing all the countries, we're just calling top 3. Let's try and shorten our work. We can probably use a function method, which we can call it every time we want it. So let me define the function. So we can call it define, and we want top 3 countries. So let's name it top 3. And here we'll take input as our data, like our data. And we want input again as parameter, like column, for which we require top 3 countries. Now here I'm going to do like year list. So year list is nothing but all the years into consideration. So we have data, which we take, and from the data we'll also take year, right? Now that year will be, and now we know that in our data, year date time data type. So we'll call it date and year. By this, we are only extracting the year of a component and not just the date or month, because we are interested in year, and we'll sort our values. Sort values here, and we're interested in to take only the unique values out of it, right? We're also calling our result df, right? And we'll name our result df as pd.dataframe here. And we'll put the name of our columns, which is so apd.dataframe, our columns is our year list, right? And that's the That's the column we want, because for each of the year, we wanted to see what are the top 3 countries, and the index will be the top 3. So we'll keep our index as 1, 2, and 3. Now this is a banned data frame so far. We're going to fill this data frame with the help of following for loop. So we'll say that for I, or rather for year in year list, so it will iterate to each year in that year list, and we'll say that df year object is nothing but the data which we provide, and within the data we'll filter the data with the help of year. I will call it, right, since it's a datetime object, we need to do it differently. We'll call it dt.year, and we'll check whether it's matching to that particular year, and we'll filter this data. That's our df year data, and this is a value that we're going to add. So we'll say df year, right? From that year, we want to create group by object. So we'll call group by, and we'll say group by this data with the help of country, right? And use the particular parameter. So what are the parameter value which we are providing? Group by country, and give us the parameter value in terms of sum, and sort that to values, right? And descending order basically. Sending is equal to false, right? And give me only the top 3 values and provide me index of it. So let me show you this entire snippet of code. How does it work, right? So for example, if we take this df year, let's say our DFF, that's our data frame, right? Now in the DFF data frame, let's take year, right? And let's call it dd dot year is equal to 2015. So this will only give me data of 2015 if I call it under DFF. If I do that, this will only going to give me the data of year 2015 for all the countries, right? Now, what it does here is if I take this particular data like df year, right? If I do it group by, so let me just copy this group by and show you how does it work. So if I do that group by country, right? And instead of parameter, if I say, let's say life expectancy, and if I do this, this is going to give me this 3, right? If I don't do this, let me just show you the sum, right? So if I do that, it will give me all the countries and their life expectancy value of year 2015, right? Now we want top 3 countries, right? So we need to do the sort by. So that's why we are doing sort values, and ascending is equal to false. That means it will give us the descending order. So once I do that, it will give me that Japan, Italy, and Australia is having the highest expectancy. Now what I want is not this numbers, but only the name of the country, right? So that's where if I do just head 3, that means it will pick up only the top 3, and it will only give me the index. So it will only pick up the Japan, Italy, and Australia, and not that number. So when I execute this, it's going to give me this list. These are the top 3 countries, right? So I'm putting the same snippet of code here, and that will be our value. Now this value, I am appending each year in our final data frame, right? Where we are going to store that value, right? And this will iterate for each year and for each column, right? And let's do it. So we'll say result.df, and we'll call it that particular year in which it's going to store it. So year into consideration, and that's nothing but our value, right? And this particular code will also return me the result df, right? And let's run this, right? And let me delete this cell for you. Okay, so our function is ready. It will practically not give us any output till the time we apply this function on a column and providing input of data. Okay, so before applying this column, since we want to iterate through each of the parameter, we need to again run one more loop here. So for that, let me import this IPython, because we wanted to display it in a better way where we can see it. So we can use this module called IPython. And from IPython, we can use display as a sub library, and we can import display. right? And let's import this. Right, this will help us to beautifully look our data frame, which we're going to run it in a loop, right? So we'll say that for I in selected column, so it will take all selected columns and it will iterate to each of that parameter, and we'll say that result is equal to top 3. Now we are calling this our function that we defined, top 3, and here we are providing our data, that's DFF, and the parameter is nothing but I. So it will take each parameter and it will give us the top 3 countries for each of the year for each of the parameter, right? And we are again going and print I, right? That's the name of the column, and that will display the result. So that's the data frame. Right, and again, let's print maybe a separator to keep it more visually appealing. And as we execute this, it is executed for all the columns. So as we see inflation rate, these are the top 3 countries were having the highest inflation rate. In 2015, it was Brazil, Turkey, and Indonesia, all the way to 2020, where Turkey is highest in terms of inflation rate, and India is the second highest inflation rate, so as the Saudi Arabia is the third highest. Now, similarly, if you want to see the life expectancy, it was the highest in Japan way back in 2050. 2020, again, Japan is leading all the way in terms of life expectancy. But as you see, Australia has taken over Italy, and it's now at number 2 in terms of life expectancy, while Italy has dropped from number 2 to number 3. Similarly, if we see the mobile phone subscription, South Africa is the top, holding the top position since 2018, and Japan is at number 2 and Indonesia is at number 3. If you see the foreign direct investment, Germany is at number 1 in year 2020, Mexico is at number 2, and Brazil is at number 3. Similarly, you can see for all the columns that we have, for all the years, we have the top 3 countries. What you can do from your end is try and define a function which will give us the bottom 3 countries for all the parameters. Try and make your own code and try and run it. Try and get this kind of results. Now, this is more insightful when you try and present it to the business partner, right? Moving forward, okay. Now, let's understand life expectancy in more detail. But before we go there, let's create one more column called year only. Right, and this year only will be just the DFF, and we'll take the year as a column, and from there we call in TT, and we call date, and we'll call only the year to store only the year value, because eventually we need to use this particular column. And if you see DFF dot head, you see that the year value is only the integer value that we have, right? Moving forward, let's understand the life expectancy. For that, we need to understand and create our own data using pivot table. So we can use pd.pivot table. If you have used Excel sheet, you must be aware about the pivot table. If not, it's okay. Pivot table is a great method to visualize and to analyze your data. It will pivot around 1, 2, or multiple columns, and it will give you values across other columns by grouping to that particular pivot column. So here we are going to use pivot table. Within the pivot table, our columns will be year that we are going to use. So it will be year underscore O that we're going to use. Our index we want is country. Our values that we're going to use are life expectancy, and the data which we are going to use is DFF. Since we are using values here, we need to provide the input for aggregate function. We're going to use mean. We know that for each of the country, for each of the year, you have only one record, so it doesn't matter whether you use mean or sum. So we are going ahead with the mean for now, right? And we are rounding off our data to 1 decimal place. So as we execute this will give us the pivot table for all the years, for all the countries and their life expectancy rate in each of the year. Now, since it's just a display of the data, we have not stored this data. So let's create an object called life underscore expectancy. and store this particular data frame in life expectancy data frame, right? And once we do that, it gives us the life expectancy object. Now, we also want a percentage change. So we wanted to see how this particular life expectancy is changed from 2015 to 2020. So here we are going to call life expectancy, and we are going to introduce a new column called percentage change. So percentage underscore change. And here we're going to call life expectancy and calling a column like 2020, right? And let me copy this and minus the life expectancy in year 2015, multiply it with 100 and divided it with life expectancy of year 2015. That's our base year. So it will show us the percentage change from 2015 to 2020. And probably we can round it off the entire data to make it more readable. Maybe round it off to one decimal place. Okay. As we execute it, we can see life expectancy now, and we can call life expectancy. As we see that there is a percentage change. Now we can sort this value. So we can do sort underscore values, and we can provide ascending equal to ascending is equal to false. And here we can provide sort to values by percentage change. So we can call percentage change. And as we do that, we get this values sorted out in descending order. Right? And we can store this again as life expectancy object. So once we do that, we practically have the life expectancy table. South Africa is having the highest percentage change in terms of life expectancy. It has improved a lot. While if you see the Mexico, where life expectancy has been reduced from 74.7 years, it has decreased to 70 years in 2020, so which is performing very badly. There are a couple of countries where there is not much of change, like France and United Kingdom, where you find the percentage change is as low as minus 0.01. Now, if you want to visualize this particular table in bar graph, that's a good way to go about it. And let's do that. So we'll call plt.figure, and we provide fixed size. Here, that fixed size is 11 by 5, let's say, and we can call sns.barplot here. And on x-axis, we provide our life expectancy dot index, right? And on y-axis, we want our life expectancy, and we want maybe percentage change. We can use different color palette. Here we're going to use maybe what it is, and can give title to our plot. Percentage change in life expectancy from 2015 to 2020, and plt.xtix. We can give a rotation again of 90 degree, and we can do plt.show. As we execute, we can see a nice graph for the table, data table which you've seen above, like South Africa, China, Australia are doing good in terms of percentage change in life expectancy for all these 5 years, while Mexico, United States, and Indonesia are not doing that great, and they are in the bottom 3 in terms of life expectancy. Right? Similar to the life expectancy, we can also understand a couple of more parameters, let's say foreign direct investment, and we can simply just copy this particular piece of code here that we have, and we can use it to create code for foreign direct investment. So here we say that FDI and basically want year, country remains the same. Instead of value as life expectancy, we can use columns. So we can call our dff.columns and simply copy the columns from there. As you see that we are interested in foreign direct investment, so just copy this column here, name of the column, and in value we can put the foreign direct investment. data is practically DFF, and we also wanted the mean value with rounded to 1 digit. Simply copy the other lines of code that we did, right? And we'll show you. Let me copy this first and paste it here. Right, and here we want again FDI. So FDI in percentage change, that's my FDI in year 2015. Sorry, 2020 here, minus FDI in 2015. Again, my base year is 2015, so it's FDI 2015 rounded up to 1 digit. There are a few more lines of code that we're going to copy it. As we do that, now here FDI is again nothing but sorted out by percentage change, right? As we do that, we can see that our FDI table is basically the same table for all the years where we see the percentage change for all the countries. Japan is having the highest percentage change from 0.1 to it has gone all the way to 1.2, while Italy from 0.7 it has gone down to as low as minus 1.2, and the FDI has shrunk to 271% between this time frame. If you want to visualize this data again in terms of like this graph, we can simply copy this code snippet here and we can paste it here. Here, instead of life expectancy, we just need to change the name of the object, and that's FDI. And that's the beauty of the code. You can use it for multiple columns. You can even draft a loop and create all the pivot table and create fancy charts for all the columns you have, right? And here we're going to use maybe Violet called rocket R and percentage change in probably FDI. Right, I have to execute this. This is going to give me the percentage change in FDI, and as we see that Japan is at top, and country like Italy and United States and France are not doing that great amongst the G20 country that is available. And you can do it for so many other varieties of columns that is available with us. Moving forward, let's do some feature engineering. Let's try and create additional columns. So let's understand the EXIM. EXIM is nothing but it's a short form of export and import. Let's try and understand the EXIM balance. So how do we define EXIM balance? Is the exports minus imports. So we're going to see the net of export minus import, so that we name it as an EXIM. And this is how we do it. So we'll call it DFF, and we create column called net EXIM balance. And this net EXIM balance is nothing but DFF of export of goods and services minus DFF of import goods and services, right? And if you execute this and see it DFF dot head, we see that now in our DFF dot head, you see that there are a couple of columns there before the net EXIM balance, set the column which we have created, right? So let's use this. Let's define pivot table, same way which we did. So we say pvd dot pivot table here, and we want our index as country, and we say our columns as year, and we want to values as net EXIM balance that we created just now, and we're using aggregate function. Aggregate function again doesn't matter. So one record for each year for each country. It should be okay. Using mean, and in which case we are using DFF as our data, and we'll round it off with 2 units, right? And we're saving this as an EXIM data frame here. Let's execute this. As we do that, you see that for each of the year and for each of the country, we find the EXIM balance for each of the country and how it has moved forward. Let's visualize this data in a line plot, because this is a continuous series in terms of data frame. It went from 2015 to 2020. So let's see for a few of the countries. Let's say Latin American countries. So Argentina, Brazil, and Mexico. Let's take this 3 countries and see that how their EXIM balance has progressed from 2015 to 2020, maybe using a line chart. So let's call a line chart. So we'll call plt.figure to set our figure first. And we can call fixed size. Fixed size, let's say 10 by 4 units. And here we call sns.lineplot. And within sns.lineplot, our x is year. Our y is, let's say, our net EXIM balance. And our data is equal to DFF. And we'll call within DFF, we want DFF where country is in, and is in, let's say, a set of Argentina, Brazil, and Mexico, right? And so that we also want hue by, let's say, country to differentiate between colors. We also don't want confidence interval, so let's keep ci is equal to false. And let's do pmt.show. So we do that. We can see that, okay, country Argentina, which is in blue color, till 2017 it was dropping. And from 2017, it started improving. 2018, 2019 has seen a big, huge, humongous growth in terms of net EXIM balance. And then in 2020, it's dropped, right? Similarly, if you see in terms of Brazil has improved. It was more steady in year 2019. From 2019, it has started growing. Similarly, Mexico, from 2018, it has started picking up. So all the South American countries from 2018 onwards started picking up. That's a general trend you can observe. Similarly, we can use this particular code snippet, paste it here, and we can do probably for other countries, like instead of Argentina, Brazil, and Mexico, like South American countries, we can use it maybe for, let's say, Canada here, and let's say United States, to see the Americas region, how they are performing. So if you see, they're both going down from 2019 onwards, and it's been a steady increase all the years till 2019, but from 2019 we're seeing 1 year of downtrend. So this is practically a line chart for you, each of the country for net EXIM balance, the feature which you have created out of export and import. There are a host of other columns which is available. You can create your own feature and try and visualize in terms of different graphs and gather more insights out of it. Once you practice this data, and kindly do share your insights in the comment down below, and do also let me know what type of other projects you would like me to cover so that I can prepare my next video on those lines. This is a part 2 of our video. In next video, we are going to use this data and create more effective visualization, more interactive visualization with the help of Tableau. But for now, I'm stopping it here. I'll see you in my next video. Bye-bye. Thanks for watching.
Please like, share, and subscribe my channel. Thanks for watching. Bye-bye.